So today in this video I'm going to work a problem related to linear momentum. But before we get started, I thought it would be good to revisit very quickly what linear momentum is in the general mathematical case before we get started. So here we have a faucet, and this is a real life case in which we can observe fluid having a momentum as it flows through this faucet. Basically we would expect linear momentum to be conserved along this part of the fluid flow, but then it hits the nozzle and it changes speed and changes direction. And what we know a change in speed or a change in direction to be is an acceleration. And since the fluid is accelerating, changing speed or changing direction, we know a force is being exerted on it. And these linear momentum problems that we work in class relate a change in momentum to the forces exerted on the fluid. So that's what we're going to see now. So now we're ready to work a problem related to the conservation of linear momentum. And the problem that I'm going to work out here is problem 40 from textbook chapter 5. And it's very similar to the water flowing through the nozzle in the faucet, because we have in here a pipe with water flowing through it, and a bend occurs in the pipe, and then the water exits the atmosphere. It tells us that this right here is a free surface. So we're going to go ahead and begin solving it with the data it gives you. And there, of course, are two reaction forces holding this system in place, because if there weren't, once again, since we have this change in the momentum and in the direction of the fluid flow, the motion of the fluid, we're going to have to exert some forces to keep the whole thing in equilibrium. And the two things that the problem asks for, it asks for one, the flow rate through the pipe, and two, it asks for the vertical component of the resultant force that is holding the system in place. So there's a certain order I'm going to do the steps of this problem in. And the first thing I'm going to do in any conservation of linear momentum problem is define a control volume. And that'll look like this. And you can see that it looks exactly like the figure that it gave me above. And I'm going to put these black lines along the boundary, which is a fixed boundary, and this is the boundary across which no fluid flows, because it is the physical boundary of the pipe. And then to the free surfaces, or to the surfaces which the fluid can flow across, I'm going to attach a normal unit vector. And this normal unit vector represents the surface area across which we can have a flux right here, and it is always attached normal. The two things that are very important in drawing this normal unit vector are, one, that it is perpendicular to the area which it represents, and two, that it points out. Both of them are pointing away from the volume that is enclosed by this red dotted line, this boundary. And then on this figure as well, what I also want to represent are my velocities. So here I have fluid coming in. We'll call this V1, and this is surface 1, surface 2, and then here I have V2. And then in the back of my mind, I know that I also have pressures exerted at both faces. Most importantly, I'm going to have a pressure here. So if this gauge at this surface right here reads 10 psi, then I'm going to have a 10 psi force. That is we'll call it P1, acting right here. Now, of course, there is, atmospheric force acting everywhere, but since it is acting everywhere, it all cancels out. Whenever we're considering forces and looking at a free body diagram, we're usually interested in the net effect, as we are here. So this only place where I have a difference in pressure is right here. It's a 10 psi pressure difference from everywhere else. So now I've drawn my control volume, and I'm ready to start solving the problem. So step 2 is to consider conservation of mass, or continuity as we know it. And we remember from class that it's given by this formula, where it's the time rate of change of the amount of stuff in a control volume plus the time rate of change, or just the rate of change of stuff leaving or entering the control volume, is equal to 0. That we have to account for, or that everything that comes in and leaves has to account for the change in how much is there within our control area and our control volume. So the problem tells us that the fluid flow is steady, so we can get rid of this term, and we're now just dealing with this. And we can jump straight to the conclusion, or straight to what we know the meaning of this to be, in that, you know, m dot 1 equals m dot 2, or q1 is equal to q2, or q is equal to q. So conservation of mass, since the density in here is not changing, that the flow here is equal to the flow there. So q1 is equal to q2 is equal to q, which means also that what we know Q to be, V1A1 is equal to V2A2. So V2 is equal to V1A1 over A2, which is V1 times, it says 0.2 square feet over 0.1 square feet is equal to 2V1. Before I run out of room here, I'm going to go ahead and write step 3 on here as we apply conservation of momentum. But to revisit this for a second, I have neither of the velocities in this case, and I'm being asked for the Q. I'm being asked for the flow rate. So it might end up, since I know that I'm going to be dealing with velocities in my other formulas, it might end up that I need to know Q in terms of the velocity. And I can write that quite simply, because Q is equal to, well, V1A1. So if I'm trying to write the velocity in terms of Q, I get, if Q is equal to V1A1, then V1 is equal to Q over A1, and V2 is equal to Q over A2. And we're going to hold on to that for a second. So I've done my conservation of mass. I've looked at everything I can look at that might help me with having some additional information later. So I'm going to move now to the conservation of momentum. And that comes from, I guess, the Reynolds version, the Reynolds transport theorem as it relates to conservation of mass, where we have this extra velocity term in the formula. Once again, a steady flow, so we're going to disregard that part. And then we have this. And there are two parts to what is represented in this integral. There's your first rho v term, which is the stuff, you know, leaving or entering, and it is positive or negative based on the coordinate system. And then there's your v dot dA, and that is the flux of the flow across the boundary. And the reason we dot it is because we're only interested in the stuff crossing the boundary. You know, if our area is like that and we have flow that moves like this, we're only interested, you know, it has therefore components. We're not interested in the component parallel to this surface here. We're interested in the component that is crossing it. And also, even though this is integrated with respect to the area, in almost all the cases that we deal with in class, the area is constant and none of our velocities or densities are a function of the area. So we just end up with rho VVA. And we're going to take that back now to our conservation of linear momentum. So applying the conservation of momentum to this problem, we're going to have a term from the first surface and a term from the second surface. And once again, we are looking to use rho VV and A. And I think it's always beneficial to think of this in two parts. For the first surface, I like to break it into two parts because each part may have a different sign. Now, to determine the sign of the first part, the rho v term, I'm just going to look at the way the fluid is moving with respect to my coordinate system. So I'm going to assign my coordinate system to be y is positive up and x is positive to the right. And this rho v of the fluid flow is moving to the right. We're doing this in x, so I should have mentioned that already. So we're doing this in the x direction because, once again, this is linear momentum. We've got to do it in a certain direction. We're trying to conserve it in a straight line. So we're doing this in the x direction. And in x, my rho v, my flow term, or whatever you'd like to call it, is moving to the right. So it's going to be positive. Now my v dot dA term, I have to look at both my velocity, where I've drawn the velocity arrow, and the unit normal vector to the area surface that I'm crossing. And what you see is they point in opposite directions. Therefore, I have to assign a negative to this term. Basically, if you recall from the definition of the dot product, that two vectors dotted with each other is the magnitude of the first times the magnitude of the second times the cosine of the angle between them. And effectively, since these point in the opposite direction, we're taking the cosine of 180 degrees, which makes this whole quantity, well, the cosine of 180 degrees is -1, so we have a negative value. So that's the first part. And then I'm going to do it again for the second surface. The second surface, I have my rho v term, and once again, I'm trying to write rho v in terms of how the fluid is moving. And I see that my rho v isn't entirely moving in x. It's not entirely flowing in x. It's got components. If this is v2, representing like the overall flow, I've got a y component and an x component. And I'm not particularly interested in the y component because we're doing this in x. So I need just the x component. And this theta is 45 degrees, as we see from the problem. So that's what I'm going to take it to be. And I'm also going to take it to be negative because if you look, the x component of this flow here is in the negative x direction. So I'm going to have negative rho v2 cosine of 45 degrees to give me that part of my momentum term at area 2 here. And then my v dot dA portion, this is a bit simpler here. I see that v2 and the unit normal vector are pointing in the same direction, so I can have positive v2a2 here. This negative and this positive is quite important because it relates back to continuity again, where negative when they're in the opposite direction, because here I'm talking about stuff entering my control volume, and positive when they're moving in the same direction, because that means that I'm talking about stuff going out of my control volume. And that's why it is also so important that I'm always consistent about my unit normal vectors, being that they point out of or away from the control volume at the area at the surface at which they are attached. So now I have done my linear momentum portion of this problem, and I'm going to simplify it really quickly so that you see negative rho v1 v1a1 plus negative rho v2 v2 a2 cosine of 45. And I just moved this around a little bit because the other thing to notice about these terms is that v1a1 and v2a2 are q. We talked about that earlier, and that's very obvious. So I could combine these terms and go rho v squared a or rho v squared a, but it's not going to be too useful to me here because remember, I do not have any of the velocities. What I am looking for though is q. So in simplifying this again, I'm actually going to put q back in here, taking v1a1 to be q. Put some parentheses so we don't forget that they're multiplied. And that helped. But remember, I still do not have this v2. But the good thing is, as opposed to relating v1 and v2, I've got two unknown terms here. I actually got three unknown terms. I don't know q or v1 or v2, so I need to write them all in terms of the same one. And let's write them all in terms of q, since q is what I'm looking for. And we said that v1 in terms of q is q over a1, and v2 in terms of q is q over a2. So now we have negative rho v1 is q over a1 q minus rho v2 we said was q over a2 q cosine of 45 degrees. And now, one last time, we have negative rho q squared over a1 minus rho q squared over a2 cosine of 45 degrees. And from class, and in the video, we also remember that we proved that and even just from the general concept here, that the linear momentum change is equal to the sum of the forces. That is, it's the difference in the forces that is allowing for the momentum and for the quantity of the motion and for the nature of the motion to change. So this is what we're going to set it equal to. We're going to set this momentum equal to the sum of the forces. And the sum of the forces in x, of course. And the sum of the forces is quite easy because we just look at our free body diagram, not forgetting our reaction forces, and we sum them. Now, if there was a pressure 2 term here, it would be pointing perpendicular to that surface, and then we would need to get an x component of it, and multiply it by the area. But we don't need to do that because we said that P2, A2, you know, cosine of whatever is 0 because P2 is the atmosphere and it's acting everywhere. But we have a pressure at P1 and we multiply it by the area. Remember, pressure is force per unit area and we need the total force, so we multiply it by the area and get the total force. And then lastly, our other force in X is our reaction force, which by our coordinate system is pointing in the negative direction, whereas this is pointing in the positive, so we're going to subtract 1440 pounds. P1A1 is the pressure, which is 10 pounds per square inch, and I need to make that pounds per square foot because all of my other units are in feet. And then I multiply it by the area, which also in feet. That's the biggest reason. So the area at 1 is 0.2 foot squared minus 1440 pounds. And this guy we now see is in pounds. So we're now ready to go about solving this. And we're going to have 10 times 0.2 times 144 is going to be 1,4. So I can plug in numbers now and solve for Q. This is equal to that. For the sake of space, I'm just going to write rho, well, I can go 1.94 is rho, slugs per cubic feet, but I'm going to leave the units off just to save a little bit of space on my work here. A2 is 0.1 feet squared, cosine of 45 degrees. That is Q. And my final answer here is 7.01 cubic feet per second. That is my flow rate Q. Q is here and Q is there. So now the second part of the question asks us to find the vertical component of the reaction force, or of the force holding this in equilibrium. And we're going to do it the same way. But now, of course, we have from Q and from continuity, we know we have all of the values that we need on the momentum side of this equation, so that if we have an unknown or one unknown here on the right, it'll be pretty straightforward to solve for it. So let's do it. Recalling that Q is equal to 7.01 cubic feet per second. So now we're going to solve for the force in Y. And we're going to do the same thing. So on the momentum side, we've done conservation of mass. All of that stuff is still true. Doing conservation of momentum, conservation of momentum in the Y direction is a bit easier now, because at the surface 1 here, we see that we have no know anything in the y direction. Our surface here is a vertical surface, so everything crossing that boundary that we have, the pressure, the velocity 1 on a unit normal vector, are all orthogonal to y, so we can forget about all of them. So we have still at 2 a rho VVA term. We're going to look at which way the fluid is moving. V2, our rho V2 term, which way overall it's going, our scalar quantity, not our vector, our scalar quantity here, it is moving down. And it is therefore going in the negative y direction. But remember, once again, it has an x and a y component. We only want this y component. So we're going to have to get the y component, and we do that, of course, by taking the sine of 45 degrees multiplied by the hypotenuse, the overall magnitude here, and it is in the negative y direction. So negative rho V2 sine of 45 degrees. And we look at our V2A2 term, and we see that they match, that it is moving out with it. So we have just V2A2, which we can conveniently remember is Q. And that's it on the momentum side. And then we set that equal to the sum of the forces in y. And we have equals the sum of the forces in y. So a pressure that would be exerted here, but it is not, P2 times whatever it is multiplied by is going to be 0, because P2 is 0. Remember, it's the atmosphere. And then the only other force we have is this vertical component of the reaction force, FAY. And this makes it very simple to see that at first we have, or it makes it very simple to see what is happening with the fluid momentum. At first we have our rho Q over here. And remember, rho Q is m dot. It is our mass flow rate. And there's momentum in the x direction, but there is none in the y. There is none. There's no fluid motion in the y. And momentum is a measure, it is the quantity of motion of the fluid, and there is none of it in y. And then we're going to create quantity of motion in the y direction. And usually we represent momentum as the product of mass and velocity. And here we're taking, m dot v, which is what allows us to end up with a force representation, because m dot v is like the time derivative of mv, and taking the time derivative of just the velocity part is mv dot, which is ma. Just a little side note to remember what we're talking about here. But like I said, it's very easy to see that we have no momentum originally in the y direction, and we're creating some. We're creating motion in the y direction, so of course we should be able to say that there must be a force exerted in y as a result of the fact that we're creating motion in y. And the thing itself isn't moving, so all of that force, since there is no motion of our overall nozzle, overall system here, all of that force is represented in the change in the fluid flow. So the force is what we're looking for, and we have all of these variables. We have values for all of these. As opposed to trying to solve for V2 really quickly, remember we wrote V2 as Q over A2, so I'm going to write rho Q over A2 for V2. Sine of 45 degrees is equal to FAY. A2 is 0.1 foot squared to -1 because divided, and sine of 45 degrees. And I get 674.1, so 674 pounds is my vertical component of the reaction force. And that is how you perform a mathematical analysis of the conservation of linear momentum on a fluid flow with a control volume. Remember, the steps are always to define the control volume first, correctly drawing on that control volume those unit normal vectors. And then it's also useful, of course, to represent the vectors that pertain to your fluid flow and the pressure exerted on that body. Hope this helped.